second piece of the puzzle today. We've talked about Arrhenius acids and bases, Bronsted-Lowry acids and bases. Some acids and bases don't have protons to donate versus what to accept. So another definition is the Lewis acid-base definition, and this deals with electrons as opposed to protons. This is not something that's typically assessed anymore, so I think we will pass on it. The other piece we want to talk about briefly today is the common ion effect, and you already know how to predict which way equilibrium will shift based on an increase or decrease in substance. With the common ion effect, the wording is confusing. It says the suppression of the ionization of a weak acid or base by the presence of a common ion from a strong electrolyte. So that is a big mouthful, so let's keep it really simple. Here's our equilibrium hydrolysis reaction. Which way shows ionization of the weak acid, forward or backward? Forward, forward, forward. If you're ionizing the weak acid, you're going from the left to right in the forward direction. Now, if I am suppressing ionization, that is saying that which reaction is favored, forward or reverse? Reverse. What might cause suppression of the forward reaction, or another way stated, what might cause the reverse reaction to be favored?
I don't know what that's called.
This?
Acetic acid.
Yeah.
Decrease in acetic acid.
You know what?
What else?
Acetate.
Increase in acetate ion, or an acid spike, right? Increasing hydronium ion concentration. So it says acetate ion is found in both acetic acid and in sodium acetate. So if you increase, let's say, sodium acetate, you will increase acetate ion and the reverse reaction would be favored, hence suppressing ionization. Let's see what happens to the pH when you have some acetate ion already in solution. In order to do this, I want to start a little more simply. Let's say that this was our equilibrium reaction. Here's our Kb. We're leaving it as Kb because this is a weak base generating hydroxide ion. If I had a concentration of ammonia initially at 0.15 and no ammonium ion, Kb times, I just want to keep this simple for a sec. Let's say that I had ammonia and water, and we're generating ammonium ion and hydroxide ion. The Kb is 1.8 times 10 to the negative 5. If the concentration of ammonia is 0.15, to get the hydroxide ion concentration, I'd have Kb is equal to x squared over 0.15, correct? Okay, so Kb is 1.8 times 10 to the negative 5 times 0.15, and I'm going to take the square root of that to get the hydroxide ion concentration, and that would be 1.6 times 10 to the negative 3. The pOH would be negative log of 0.0016, and that would be 2.80, and the pH would be 11.20, correct? I just want a reference point. That you already know how to do. That should not be an issue. in this particular reaction, so this is if you only have ammonia and you don't have any ammonium ion or hydroxide ion, just as we had done previously. But in this example shown here, what happens, and this is written out for you in your notes, let's take a look. We've got 0.15 molar ammonia, but we also had 0.35 molar ammonium ion. How did I get that? Well, this is given. So is that concentration the same thing as the ammonium ion concentration? Yes, because it's going to ionize 1-to-1, right?
Yeah.
And that's where some of you are confused. So now for the first time, you have some ammonium ion. So for the first time, these concentrations, both initially and at equilibrium, will not be the same. Subtract, add. Why must the reaction go in the forward direction? Because you don't have any hydroxide ion. So now you get these concentrations, and again, for the first time, these are not the same. Kb is equal to this times this over this, and this is not x this time, but rather 0.35. The Kb is small, so we can eliminate anything subtracted or added to a concentration. And now when we solve for x, that's the hydroxide ion concentration right here. Well, actually, no, that's the Kb. So the x is right here, and that's the hydroxide ion concentration. Why would we get the POH? Because you are dealing with a base, you have hydroxide ion concentration. So now we have the POH. How do we get the pH? 14 minus. So this pH is 8.89. And let's do a comparison here. I'll write them side by side.
Okay. What was the 0.15 divided by 1.8 times 10 to the negative 5? What was that?
Showing you can get rid of that.
It was, no, it was just showing all the work. Here's your Kb. Here I was plugging everything in. This is the Kb.
Yeah.
I wrote it on the other side. This is this, and this
No,
is
at the
this.
top.
You just want to solve for x.
No. Up to the right.
It's showing
To the
you
right.
can get rid of
To the
that.
left, sorry. To the left.
This is just showing the 5% rule right here.
Oh, okay.
What I want to show you is that when you had this, and you had this, and you had nothing, and you knew you had to go in the forward direction, and you had this, I just want to get you, this is all written down for you, I just want to get you to this point. And I'll rewrite this since it's illegible. Alright, so this is all in your notes. What I want to show you is when you do it this way, the hydroxide ion concentration is 7.7 times 10 to the negative 6 molar. And then the pH, doing it in 2 steps, this is in your notes, is 8.89. How do these concentrations compare?
The blue first one's greater.
Really?
Oh, wait.
This is much smaller, right? You have a negative exponent. Careful, careful. And this compared to this is less basic. So this is a hard comparison to make. In any event, what happened to the concentration of hydroxide ion when you had a common ion? It did what? It decreased. And that's because initially the reaction runs in the forward direction and you get a little bit of this. But now you have quite a bit of this, which is going to result in equilibrium shifting to the reverse direction. So when you have a common ion, that effectively suppresses ionization, and you can see that because you generate a lot less hydroxide ion in this situation than you did if you had nothing here. And as a result, if you generate less hydroxide ion, the pH is going to decrease. Okay? I would like you can do it, to try this problem right here.
So we had to compare.
You might. Well, you might or you might not. You know that if you have a common ion, you'll get suppression of ionization. So while the forward reaction initially runs, once it starts to go, the reverse reaction is going to go really much faster than it would have because you have such an excess there. So if you look at this problem here, it's grossly similar. Give it a shot. I'll do it too. 5 minutes. The timing is crucial now. This one's going to be a little easier because you have an acid.
Wait, so do you use cyanide?
No, you're going to start with the acid.
Where does the potassium come from?
That's just the salt you throw in, which immediately ionizes, so you have a concentration of cyanide ion. Mm-hmm. All right, let's take a look. Here's my rice table. I'll label it up. And this on the side was to make a comparison. We'll do that in a sec. So the pH, did you get the pH?
Yeah.
Good. All right, so the percent ionization decreases with the presence of a common ion because less hydronium ion is generated due to the reverse reaction being favored once some hydronium ion is generated. Without the common ion, so if you didn't have this, hydronium ion concentration is significantly greater because more of it gets generated as you don't have that counteraction so quickly in the reverse direction. The pH would be less. But with the common ion, you get suppression of that ionization, and as a result, less hydronium ion is generated. With less hydronium being generated, the pH will be higher.
So on the previous one, even though the
Yeah, that one was a little bit tricky. Again, you'll
the
still...
hydroxide ion concentration decreased when you added more, it still remained basic. Is that because the original pH
was so basic. You got it. But in either... You want here? And again, for those of you able to do these now within 5 minutes, you did a lot of practice problems this weekend. If this looks like Chinese to you and you're like, I just can't get these problems to rip, please do not wait until Tuesday night at 9 at night, because by the time you text me, I will be in La La Land, and it's going to be too late. If you don't have a grip on what we did previously, you need that grip tonight. And this way, tomorrow, you're just reviewing. You can't first be learning the material the night before the quiz or test, which is what some of you are doing. It's really important to stay with this chapter. This is the hardest chapter of the year, and you already know that many of the chapters have been very challenging already. So please get a good basis here. In regard to your practice quiz, I'll go through what you can do at this point. These are more good problems to practice. And in regard to what we've already done and what we just did, that common ion effect packet, it's the first part of a double packet, will be very good preparation for you. You want to be able to write Ka and Kb expressions. You want to be able to solve them. You want to be able to solve them for pH. You want to be able to interpret it in regard to percent ionization and know what happens to percent ionization if you increase or decrease the concentration of the substance.